Did this. Okay. Hi everyone, and welcome to our talk, Virtualization from a Networker Point of View. So I'm Corentin Bayet. I was supposed to be here with Thomas Bouzerar, but unfortunately he had a last minute issue and couldn't come today. So I will do my best to handle his part of the talk. We both work in the reverse engineering team of Synactive, which is composed about 45 reversers, and we mainly focus on low-level research, reverse engineering, and vulnerability research. Thomas and I both presented some vulnerabilities before on hypervisors at Point 1. So a short introduction about this talk. Today we'll talk about virtualization and how it works, but we won't go deep into the details of the implementation of virtualization. We mainly focus on the attack surface that is presented by an hypervisor, and we'll review some bugs that were found in the last years in various components. And we won't go too deep into the details of the exploitation of the bugs because it's not the point of the talk. So a few definitions first. What is virtualization? Virtualization is the ability to create the illusion of having multiple computers running on the same physical hardware. So the software that is doing this is called the hypervisor. Maybe you know some so Hyper-V from Microsoft, Xen, VirtualBox, VMware Workstation. Maybe you used some before. And a specific part of the hypervisor that is responsible of managing the CPU, the memory, everything that a virtual machine needs to run. It's called the VMM, or Virtual Machine Monitor. And finally, the last definition is the guest, which is the operating system which is running inside a virtual machine. So what is a hypervisor doing? He has to do mainly three things. The first one is to virtualize the CPU and the memory that the computer needs. But it also needs to do it with the platform, so it has to handle timers, CPU traps, interruptions, everything that the computer needs. And the last thing is input-output devices, that every component that a computer might need to interact with the other computer, for example, like buses, graphics to interact with hardware, so network card, disk, everything that a computer actually needs. And it has to do this by respecting three main criteria. The first one is fidelity. You want a program running in a native, in a virtual environment to run like it was running on actual hardware. The second one is the performance. You want the majority of guest instructions to be executed by the hardware without the intervention of the VMM. So it has to be fast and use the actual hardware, so the CPU, the memory. And the last one is, of course, safety. You want all the resources between the VM remain isolated. And most importantly, you want the host to remain isolated from the guest. And of course, in this talk, we'll mainly focus on the safety part. So why I am talking of this subject to you? In our scope, the goal for an attacker is to escape from virtual machine. So from getting code execution into a virtual machine, getting code execution on the hypervisor, on the host. So it's called the VM escape, virtual machine escape, or VME. And it's a very powerful primitive, actually, that can be critical for some industries. You can think about cloud computing or hosting that use virtualization. Well, if you gain control on the hypervisor, you will have access to the data of a lot of different clients. You can think about a malware researcher that is running malware inside a virtual machine to be able to analyze it. If the malware is able to escape the virtual machine, the researcher will have big problems. And for us, security researcher, it's actually quite fun. When you're working on this subject, you can learn a lot about a real computer actually works, even if it's simplified. And you can do this only by analyzing and reversing software. So I'm more like a software guy, so it's a pretty good thing for me. And you also have to read a lot of manual, like Intel CPU manuals, but it's supposed to be part of the fun part. And it's actually quite complex, so it's a very low level. You have complex vulnerability and complex exploits, and well, personally I like it, so it's actually also in the fun part. Let's review some basic of virtualization. How does it work? So, how do we actually virtualize a CPU? The first approach chosen by VMware in the 90s was a technique called full virtualization with binary translation. In this technique, the idea is that you can directly execute unprivileged instruction of the guest directly on your CPU because you already have memory segmentations or something like that, so it's not a problem. But you can't do this with privileged instruction because if you execute those instructions like input-output interruptions that can change CPU flags or memory segmentation, you will just break the isolation. So the idea was to translate those privileged instructions into traps, let the CPU execute those instructions, and then trap into the VMM, emulate the correct behavior, and remains the execution to the guest. So the good thing about this technique that the guest OS has no idea that he's being virtualized. It's fully transparent for him, and he thinks he's running on natural hardware. And he has a very good portability. You don't have to modify the guest to do anything. You can just virtualize any x86 code. The bad things about it is that you have a very, very complex VMM. You have to translate a lot of instructions. You have to handle a lot of traps, and there's a lot of CPU overhead for privileged instructions. So in the next few years, CPU vendors started developing hardware features to help for virtualizations. So Intel called this VTX, and AMD called this AMDV. And the idea that there is now a new level of privilege in the CPU, which can be aware that he is running inside a virtual machine. And you can now execute every instruction directly on the CPU, and the CPU will know when a privileged instruction is needed, and it can handle it itself, or it can give back the execution to the hypervisor with an operation called VM exit, just exiting the virtual machine. So you still have a lot trapping because you need to emulate some behavior in the VMM, but you have still a huge performance gain. You don't have to trap all the time, and you don't have to manage the translation of instruction. Of course, it's not all available on all CPUs, but now it's available on all modern ones, on x86, and actually most modern hypervisor requires this feature to work. And the last technique I want to talk about is power virtualization. So it was a different approach developed back then to have better performance and to have a simpler VMM. The idea that instead of virtualizing everything and executing everything on the CPU, you will have an interface developed on the guest that you use to directly call the VMM. So it's called an hypercall for hypervisor call. And you just develop an interface and handle everything you need to do privileged operations directly in the VMM. So it can be a context switch, page faults, input-output operation, or just costing operation that you want to be fast. And you have a good performance with this. You have a very simple VMM. But the bad thing about it is that you have to modify the guest. For each guest you want to virtualize, you have to develop an interface and handle it on the host. So it's not portable at all, and you have to develop this interface for Windows, for Linux, and for every guest you want to virtualize. So nowadays, most hypervisors use a mix of all this feature. So as I said, hypervisors actually require the hardware-assisted virtualization to work. So for CPU, it's called VTX or AMDV. And for memory management, I will come back to it later, it's called SLAT. You still have this trap and emulate behavior. So you have the CPU that will trap itself with a VM exit operation, and the VMM will emulate the correct behavior, and go back to the VM using a VM enter operation. And of course, power virtualization is widely used to gain performance. So for costing operation, for devices like network cards, and it's not used when you have a when you need stealthy virtualization. For example, if we go back to the malware researcher type, usually when he is running a malware inside a VM, he doesn't want the malware to be aware that he's being virtualized because the malware will change his behavior. So he won't use power virtualization to make sure the malware doesn't know he's running inside a VM. Let's talk a bit about software architecture. You have two big types of hypervisor. The first one is called bare metal hypervisor, or type 1, and it runs directly on top of the hardware. Some examples of them are like the Xen, Hyper-V, VMware 6i. So you directly install the hypervisor on your hardware. The second type is called hosted hypervisor, or type 2. And the software is actually, the hypervisor software is running inside another operating system. So some example of that are like VMware Workstation or VirtualBox. Maybe if you use some hypervisor, you most likely use those one because it's more for personal use. But actually nowadays the difference between the two, there is not much difference because bare metal hypervisor actually have a base OS to handle user applications. So it will be Windows for Hyper-V or Linux-like for VMware 6i. So there was a big difference between them before the hardware features, but now it's basically the same. And on the last part, let's review this schematic about Hyper-V. So it's a Hyper-V high-level architecture. So in Hyper-V, a virtual machine is called the partition. And Hyper-V is a bare metal hypervisor, so it's installed directly on your computer. And then you have a root partition, so it's a privileged virtual machine that is running Windows. So actually, now if you're running Windows 11 on your computer, you don't have Windows installed on your computer, you have Hyper-V installed, and your Windows is running inside the root partition. It's a privileged virtual machine. And on this schema, you can also see 3 other partitions, so that are not privileged. And the thing I want you to see there is that you have this interface called VMBus, which is the power virtualization interface developed by Microsoft to enhance the performance of a virtual machine. And you can see that the third machine doesn't have it, just because he doesn't know which guest it is, like it's not precisely to Windows Linux, and the power virtualization interface is not used, but you can still have a virtual machine running. It just won't be as fast as possible, but you can still see, for example, so my researcher can use this feature. So of course, we don't want to understand everything here. I just wanted to show this schema. Yeah, just. Oof. So let's review some attack surface. So a quick summary of the components that are exposed by an hypervisor and what we can see from the guest OS. So first, I will speak about the MMU, so memory management unit. So it's inside the virtual machine monitor. And the idea is that the hypervisor needs to manage the memory used by the guest, because you want to have isolation between the virtual machines, but most importantly, you want to have isolation between the host and the guest. So to do this, the hypervisor uses something called shadow page tables, which is a mapping between the guest virtual addresses and the host physical addresses. So you can translate an address in the guest to an actual address in the RAM of the computer. But because it will be very, very slow to trap, like on every memory access, the trap to gain the actual address on the RAM and translate it and do the memory access, there are an hardware acceleration developed by CPU vendors called SLAT, or second level address translation. And yeah, so of course it has different name on Intel and AMD, because why not complicate a bit more. And how does it work basically? So you have on every CPU you have the basic first level address translation, where you have your guest virtual address that will be translated on the guest physical address. It's running on every computer, and using one of the CPU cage to do that. And now when the CPUs are also able to know that they're running inside a VM, and use a second level address translation to be able to translate the guest physical address into the host physical address, so we can really access the memory. So it was a feature developed by the CPU vendors to accelerate and ease the use of virtualization. Another attack surface is nested virtualization. So it's basically running a virtual machine inside a virtual machine. Most modern hypervisors are able to do this. And what you want to know about is that there is main data structure that is used by hypervisor to configure the CPU. The structure is called VMCS on Intel and VMCB on AMD. It's basically a big structure containing a lot of configuration information about the CPU and how you want to be to virtualize it. And there's a lot of so if you want to virtualize an hypervisor, so you want to have a nested virtualization, you need to actually emulate all the hardware features that are brought by CPUs. So you have to, under the VMX instructions, so VMenter and VMexit operation, you have to emulate the SLAT we just talked about. You have to emulate APIC. You have to emulate the shadowing of this VMCS or VMCB structure. So there's a lot of job to do, a lot of things to do. And of course, all hypervisors handle this very differently. And it's very, very complex. And when complexity increases, the attack surface increases. Inside a virtual machine, you also, like on a regular computer, buses. So a lot of hardware can be accessed via buses, like on PCI or USB interfaces. So using these buses, you can access emulated devices, or you can sometimes really access directly the hardware if it's pass-through. So you have a very wide attack surface because you can attack directly like the interface used to emulate the buses. You can attack the protocol, like directly the USB protocol or the PCI protocol, because it has to be emulated. Or you can access the emulated device, attack the emulated devices that you can access using these buses, or you can even attack the hardware if you want. So it's a very, very wide attack surface there. And but it's actually very dependent on the configuration. For example, if you want to attack the USB protocol, well, you need to have a device somewhere that is connected to some packets or something like that. So it might be very dependent on the configuration of the virtual machine. Another interface we talk about is power virtualization. So as we told before, hypervisors develop specific interfaces called hypercalls to enhance the performance of some devices. And of course, there is a lot of code specific to each hypervisor here to handle those calls. So this is another attack surface. And again, you can also access directly to the emulated devices through this interface. So yeah, and example devices are often power virtualized because they need performance are network cards, disks, audio queues, things like that. Sorry. Another part is graphic acceleration. So most modern hypervisors provide a way to share the GPU directly with the VM and between several virtual machines. Most of the time it's not enabled by default because most people don't need this. But if you want to do like gaming or computing into a virtual machine, it might be a great idea. And those interfaces are quite complex because there is a lot of 3D graphics acceleration with shaders and bitmaps and complex objects that the hypervisor needs to handle. So there were actually a lot of vulnerabilities in those interfaces, for example, on SVGA on VMware or VMSVGA on VirtualBox. Yeah, there were quite some vulnerabilities in the past. And last but not least is guest additions. So guest additions are tools to help the user interact with the VM. So it will provide you features like copy pasting, drag and drop, or shared folders. Probably you use that before if you use an hypervisor type 2 because it's mostly installed on hosted hypervisors so for personal use. So on VirtualBox, VMware Workstation, or Parallels on macOS. It used to be a very popular way to attack hypervisor because it's quite simple. It's not too complex, but there is dangerous features like sharing folders and everything. But so there was some vulnerability in the past, but it's not actually main attack surface nowadays. So to conclude on the attack surface, you have a big, complex attack surface with CPU and MMU and nested virtualization, which represent a very complex attack surface. So it's both complex from the defender, from the developer point of view, but also from the attacker point of view. It's because it's very complex. Vulnerability in those components are very, very powerful. Like if you break the MMU or you break the CPU isolation, you basically control the host, which you already won. But it's, yeah, as I said, it's very time consuming, very complex. So it does not represent the main attack surface chosen by attackers. Or at least it's not, doesn't represent the main, vulnerability, the most amount of vulnerability disclosed. Maybe there is a lot of vulnerability found, but nobody disclosed it. So yeah, most vulnerabilities disclosed are in the emulated or power virtualized devices, because it represents the main attack surface, because there's a lot of code there, and it's less complex. You can have classic C bugs like buffer overflows, integer overflows, use after freeze, and you don't really have to understand every mechanism of the virtualization to start finding and exploiting bugs in this, because it's just classic C bugs. You just have to understand how to communicate with interfaces. Of course, it's less stylish and it's very dependent of the it can be very dependent of the configuration, but it's easier to find bugs there. And yeah, we presented the attack surface. Now let's review some bugs actually found in hypervisor in the last years. So if we go back to our schema, we'll first start with a network service bug, because it actually exists. The bug we want to talk about was a remote code execution in the OpenSLP service. So it was a service running on VMware ES6i. This service was reachable by default from the VM and from the administration interface. And it was exploited for the first time at the Tianfu Cup 2019. So Tianfu Cup is a contest like Pong-Tuan, but it's in China. And so it was revealed at this competition, and after the contest, I actually developed the one-day exploit for this vulnerability when it was released, because it was interesting for me. And while doing this, I found multiple other vulnerabilities in the same service, but actually they were really obvious. So a lot of researchers also find those vulnerabilities, and they were reported quite quickly to VMware. And all of those bugs were actively exploited in the wild as one-days. And it became one of the biggest ones from where we had an ES6i and the last were called ES6i ARGs. And, but actually it was mostly exploited from administration interface, because, companies will expose, their administration interface of ES6i on their internal network or directly in the internet, because why not? And, but it's not actually a virtualization bug. Like, even if it had a big impact, it's not the bug we want to talk about today. So let's just skip it and remove the network service attack surface. And let's focus on an actual virtualization bug. The first one I want to talk about is affecting the MMIO parts and able to exploit a vulnerability in an emulated device. So what is an MMIO? MMIO is for memory mapped IO, is a mechanism to be able to, so it's actually a memory range, and the guest can read and write from it. And when he does this, the host will trap and call a callback and do something. And most of the time, the guest will provide a buffer when he can read, or when the host can read and write from it. So it's to pass data, to transfer data. And usually you use DMA for this because DMA is just a shared memory between the host and the guest. So the correct behavior, the guest will write in the memory range and provide a GMA range address. The host will execute a callback. He will just write the result or read some information in the GMA range. And it will give back the execution to the guest. The guest will read the result from the GMA range, and everything is fine. Everybody works as intended. But what's happening if the guest doesn't provide a GMA range as an argument, but he provides a MMIO range? So the same thing will happen. The guest writes in the MMIO, the host executes the callback, and because the guest provided an MMIO range, the host will write back in the MMIO. But by doing this, for some reason, if the hypervisor doesn't check, or it can be an unintended behavior, well, the host will call another callback, because you just wrote in the MMIO, and do some things. And this can have unexpected behavior that was not planned by the developers. And for example, this callback can free some structures that are currently used, like free the whole device state. And when it comes back to the first handler, well, everything has been freed, and you have a use data free. So, of course, this pattern, the recursive MMIO, the fact that MMIO can be called back from the host, is not a vulnerability itself, but it's a vulnerability pattern you have to keep in mind when you're looking for vulnerabilities in devices, because it can have unexpected behavior. And this pattern is exactly what happened in QEMU. So a vulnerability of this type was found in the USB emulation of QEMU, so USB 2.0. And in the exploit, the idea that you could set the transfer buffer, so where the data of the packets are, pointing to MMIO range, and trigger the sound of the packets. So the QEMU will trap into the host, will start trying to map the packet with USB packet map. And while doing this, it will trigger an error on the second packet because it's already mapped or something. And while handling the error, it will write back into the MMIO range and trigger another callback. And if the attacker does a good job, it will call the EHC reset function that will, as we said earlier, free all the device structure, freeze all the device state. And when it comes back to the first handler, it will use all the structures in use after free. So it's not quite easy to exploit, but it's a very interesting pattern. And you can read more about this in this paper called Matryoshka Trap. Yeah. So this was a first vulnerability, vulnerability you can find in hypervisors. Another one very classic is affecting an emulated device. It was actually found by Thomas, which isn't here to talk about it. And it was in the emulation of the TPM device on VirtualBox. So now, since Windows 11, you need a TPM on your computer to run. So if you want to virtualize Windows 11, you need a TPM device. So it's quite new code. And in this function, you can see, so this function is just a transfer buffer between the device, the TPM device and the guest. And this function will try to copy some data from the guest. And as you can see, there's a mem copy and there's actually no check of the size of the destination, compared to the size of the copy. So it's a very, very classic, stack buffer overflow. It's difficult to have a more classic vulnerability. And it's quite obvious actually, because in the function there is no way for the function to check the size of the destination. So yeah, this vulnerability alone was not enough because you need to leak some data to retrieve the stack cookies and everything to break the ISLR. So another bug was found also in VirtualBox, affecting the DMA part and also an emulated device. So this bug was found in low-level API called PGM fizz read, which is called when the device needs to read memory from the guest. So using DMA, because DMA is shared memory. So in this function, the host, so the function will walk the memory, the guest memory page by page and copy the data page by page. But if it encounters an MMIO range, like we saw before, well, it will call the MMIO callback and to get the data that it needs. The issue is that if the MMIO callback fails, the API will fail early and will let the last buffer uninitialized. So how does it work? You have your destination buffer and the passed as an argument of the function, and you have a GMA range address, and first page is normal, everything is correct, so the data is copied to the destination buffer. Same for the second page. And for some reason, the third page it's in a memory range. So a callback, MIO callback will be called. And for some reason, this callback will fail. And so the function will fill the remaining of the rest of the page with FF bytes, but it will leave the last page uninitialized. So the destination buffer can be used uninitialized. And some devices might a lot of devices are using this function because it's a basic function to read the MI. And because this last page is left uninitialized, some device can use it and read back it to guest memory. And by doing that, you can have, you can leak uninitialized data to the guest. And it actually allows you to leak either heap or stack data. So you can use it to break SLR or to leak the stack cookies if you need. And chain with the TPM stack buffer overflow we presented earlier, you can just have a full exploit. So a classic stack overflow exploitation, overwrite the return address, build a web chain, and get code execution on the host. And so this bug chain was presented by Thomas at Point One earlier this year, and he successfully escaped from VirtualBox with it. So those bugs were actually quite classic bugs in virtualization. So it's in the simple components of an hypervisor, so emulated device buses where we have very classic vulnerabilities. So use after free and buffer overflows. But let's dive a deep more into nested virtualization. So as we told earlier, nested virtualization is the ability to run a virtual machine inside another virtual machine, and the hypervisor has a lot of job to do to be able to do this. And if you remind, when you have to handle the VMCB configuration, which is the big structure that is used to configure the CPU, and QEMU will do this by fetching the VMCB configuration twice. So it will first fetch it from the guest to check the values to make sure everything is all right, and it will fetch it a second time from the guest to actually set the configuration in the hypervisor. So this is a quite classic double fetch vulnerability or talk-to vulnerability, where the guest can race the host and change the data in between, and you can just bypass the checks that were done in the first fetch. So this primitive gives you access to the host MSR register. Will just basically give you the control on the segmentation of the memory. And it's not, of course, trivial to exploit, but it is exploitable, and it was found and exploited by Felix Willem from Project Zero. And as he affected the VMCB configuration, it only affected AMD CPUs, so it can be very hardware dependent. And the last bug, so we reviewed most of the attack surface. Of course, we can't do everything. And the last thing I want to talk about is hardware and CPU bugs. But of course, hardware cannot be trusted, and CPUs are not immune to bugs. And when you have bugs into CPUs, some of them can be exploited from the guest to either break the host guest isolation or to break the inter-VM isolation. So a well-known example is Meltdown on Spectre, which were exploitable from the guest memory. Another example is L1 terminal fault, which also was exploited from guests. And of course, we won't go deep into the technical details of these bugs because it's very complex and I don't understand them actually. But what you want to know about this is that the root causes of these bugs are often due to performance features, because CPU vendors want to be fast and they implement performance features, and it can trigger implement some bugs in it between races of different components or things like that. So the fix of those bugs are often a performance trade-off. And since CPU vendors will always try to be faster, they will always implement new performance feature with more likely bugs in it. So it will always be an interesting attack surface, even if it's quite complicated. So to conclude, the hypervisor exposes a very, very wide and complex attack surface. Most disclosed vulnerability you can find reside in emulated and paravirtualized devices, like the bug I presented in the TPM device or the MMIO emulation. Because it's way simpler to approach for an attacker, because you have classic C bugs and you don't have to understand everything about virtualization to handle bugs here. But you still have to keep in mind the context, because it can expose some very specific vulnerabilities. Like when you think about recursive MMIO, you can have classic C bugs like use after free, but you have to know the context and know that some features can be exploited to trigger some weird bugs. Of course, you can have weird emulation bugs, hardware bugs that are very, very complex. And all of this was just a short introduction because we don't have much time. There is much more to say on the subject, to learn on the subject. And now, if it was interesting to you, I'll just invite you to try it yourself because it's fun. It can be actually lucrative if you see the bug bounty program of Hyper-V or Pontoon. And you can start by looking into emulated device because it's not that complicated. And there's a few links if you want to know more. So it's just a few links. You have, of course, a lot more to read, but it was actually used to prepare this talk. And yeah, if you have some questions, I'll be happy to answer it.
Okay, so let's thank the speaker. We have time for one question, so take the opportunity to take one question. Okay. Yes.
Thank you. How do you approach debugging in those bare metal hypervisor?
So it's very dependent on the hypervisor, but actually, if you think about bare metal hypervisors, there's features developed by the hypervisor to be able to do this. For example, on VMware EA6i, you can, when you install it on your computer, you can debug it via COM interface or something like that. And there is actually a specific debugger developed for Hyper-V or something like that. So it's doable. You can do it via COM interface or via Ethernet. You just have to enable it actually. So there is tools existing to do this.
Okay, thank you.